remember, if you want to get an interference pattern, then the double slits that you use, the gap between them has to be about the same size as the wavelength that you're using. And that is a very small wavelength. In fact, it's so small, it's about the same size as the gap between atoms in a material. And so that's what you have to use. That if you want to get a diffraction pattern with these electrons, you're going to have to use a piece of material, and the gaps between the atoms are going to be your slits. Now, if you want a constant difference, if you want the same distance between all the atoms in your material, then you need a crystal, or you need something like a piece of graphite. So in other words, you need a material that has a lattice-like structure. All the atoms are the same distance apart from each other. But notice also here that we don't just have vertical slits like we had for our light experiment, because you can't get materials where the atoms are sort of right beside each other in one direction and then apart in another one. So what you get is slits that way, but you've also got slits that way. And so you're going to get diffraction in two directions. And so what does the interference pattern look like? Well, it's not going to be, remember, if you have just slits in one direction, then your interference pattern is a series of bright and dark fringes. The 2D version of that is bright and dark rings. You get your fringes are concentric circles. But the same formula applies. So remember, X is the slit spacing, so that's this distance here, and then lambda's the de Broglie wavelength now. D is the distance from the slits to the screen, and I said X there. This is A, the slit spacing, and then X is the fringe spacing. So that's this distance, bright to dark, bright to bright, bright to bright. So if you change, say, the wavelength here, then you're going to change X, the distance between the rings. And that is what this question is asking about. Okay, so we're going to increase the potential difference. So we go back to our earlier calculations. This is all part of the same question. So if we had increased our potential difference, we'd have got a bigger kinetic energy. And if we'd got a bigger kinetic energy, we'd have got a bigger speed. And if we've got a bigger speed, we'd have got a smaller wavelength. And that's the first mark, is for saying all of what we've just said there. In fact, any of what we've just said there. Okay, so if we have a smaller wavelength, what happens then? Well, a smaller wavelength where we have not changed the slit spacing and we have not changed the distance slits to screen is going to mean a smaller X, a smaller fringe spacing. And so our rings are going to get closer together for the second mark.